A Python model of our solar system in 5 steps. So, step 1. I obtained the data from the NASA website. I'll put a clickable link in the description below the video. Using this form on the web page, I was able to get 8 files of data, 1 file for each planet. In order to use this data in my Python program, I had to convert the solar ecliptic coordinates to rectangular coordinates, which brings me to step 2. The solar ecliptic data obtained from nasa.gov looks like this. Shown here is the LSD file for the Earth's positional data in 2013. There are 5 columns. The first 2 give us the date, and the next 3 give us the solar ecliptic coordinates. These 3 columns are AU, ELAT, and ELON. The solar ecliptic coordinate system has the Sun at the origin. The AU column gives us the distance from the Sun to the planet. In the diagram it is labeled R. The ELAT column gives us the angle between the line that joins the Sun and the planet and the plane of the ecliptic. Let's call it theta. The angle through which the planet moves from the x-axis is given by the ELON column. I'll call it alpha. With a little bit of algebra and trigonometry, we can find the rectangular coordinate. Using this mathematics, I wrote a computer program separate from the solar system simulation to read the solar ecliptic coordinates obtained from nasa.gov, convert them to rectangular coordinates, and write them to a CSV file. The most important part of that program is the function that converts the solar ecliptic coordinates to the rectangular coordinate. For the simulation to work, I need the first 2 planetary positions. I used the solar ecliptic coordinates obtained from nasa.gov for this. But those positions are solar ecliptic coordinates. So we need to iterate through that dictionary using the function we saw earlier that converts them into rectangular coordinates. And here's the line of code that iterates through the dictionary of solar ecliptic coordinates. The conversion function returns the positions as vectors, so the result is a new dictionary of rectangular coordinates as vectors. The next line of code adds the Sun's position to this dictionary. Just to make it really clear what is inside that dictionary, I printed it and pasted the output into a VPython code window so I could show it to you in color. The solar system program uses a lot of dictionaries. To make the code easier to read, I wrote some functions to retrieve values from those dictionaries. I wrote a function called planetRi to retrieve a planet's initial position from the rect positions dictionary. I also wrote a function to get the initial velocity from the rect positions vector. There are no velocity vectors in the rect positions dictionary, but remember, average velocity is just the rate of change of position. This is the function that will calculate the initial velocities for all 8 planets. There are 3 other dictionaries in the program: radiuses with a corresponding retrieval function called planetRadius, masses with a corresponding retrieval function called planetMass, and colors. In addition to the dictionaries, I also have a Python list to store the planet names. Many of the dictionaries contain data for the Sun, but in some cases I need to get all the planet data from the dictionaries without getting the data for the Sun. Iterating through the planet names list allows me to do that. For example, the spheres for all the planets are created with a list comprehension by iterating through the planet names list. All the initial properties of the sphere are set using the functions I created to access the dictionary values. A sphere for the Sun is created separately. Now I can use that list of spheres in 2 separate list comprehensions to create a list of trails for the planet orbits and a list of arrow objects to provide a visual representation of the net force acting on each planet. The solar system simulation makes the simplified assumption that the only force acting on each planet is the force of gravity by the enormous Sun. So we need a function to implement Newton's universal law of gravitation. This function takes a single parameter, which is a sphere object representing a planet. This is by design so that later in the program, when iterating through sphere objects inside a loop with incrementing values of time, the function can access 2 properties of the sphere: the planet's position at a given point in time and its mass. The solar system simulation also needs to consider Newton's second law to update each planet's velocity. There's a function for that, and it needs to use that new velocity to update the planet's position. And there's a function for that. Now to put it all together. I choose to run the program to get only a year's worth of data, so that I can compare it with the data I obtained from nasa.gov, and also see how far the other planets travel in the duration of an Earth year. Inside the while loop, the program also loops through the sphere objects using the range function. By using the for loop with the range function, I am permitted, by the rules of Python, to use code inside the loop to update properties of the sphere object. The gravity is updated. Recall that this function takes a sphere object as its only parameter and updates the gravity based on the planet's current position. Next, functions are called to update the velocity and the position. Similar code updates the orbits and the arrows that represent the gravity. A few things to note about this. I only ran the program for 1 Earth year, enough time for the Earth to go around the Sun once. We can see from the result that the outer planets have a much longer year than Earth. The planet sizes are drawn to scale with each other, and the orbit sizes are drawn to scale with each other. But the planets are not to scale with the orbits. The planets are so much smaller than the orbits that it would not be possible to see them if the entire model was drawn to scale. The arrows that represent the force of gravity by the Sun are also drawn to scale, but only with each other. I compared the X, Y, and Z coordinates generated by the Python program with the data obtained from nasa.gov. Here's the comparison for Mercury. The solid blue line shows the NASA data for X, and the dotted blue line shows the data generated by my program. Similarly, red shows Y, and orange shows Z. All the planets match pretty well, at least for the year shown here. I did notice that the planets started to detract from the NASA data over time, probably because there was not enough precision with the initial points and because delta t was not small enough. Thank you for watching.